Okay, welcome back, gang. We're about to get stuck into some GAMSAT questions. It's the GAMSAT practice test A, and I'm going to be starting from where I left off last time. So, question 25 to 27. I am not going to share the questions just so I don't get flagged. But if you have this book, feel free to study along. Join the live stream, and you can comment or join the Discord, and you can study live as well. Those two links are underneath the video description. So get involved. The grind of this GAMSAT, and we're on session 50 at the moment. So we've come a long way, but we've still got a long way ahead of us as well. So get involved, get a study group happening, um, help each other out, all that stuff. Okay, we'll go about. Actually, what I'm gonna do, I'm gonna do a little bit of Jim's GAMSAT stuff, and then we'll get stuck into some questions. Just a short session, like 30, 45 minutes or something like that. So we'll finish off this chemistry section. I didn't really understand much about the um, like the reactions and redox reactions and electrochemistry stuff, but maybe if it comes up in a question, I'll come back to it, I guess.
So when we have a reaction, at the very start, it's quite erratic, but over time, it tends to just equilibrate. And what we're going to talk about today is these equilibrium constants and how you can interpret them. So let's just imagine we put some HCl into some water. We know that HCl is an acid, and we know that that means it's going to want to donate that hydrogen ion and split into its hydrogen ion and the Cl minus. So when we put it in, it's immediately going to drop down, and it's probably going to be quite steep and violent and severe. And then it's going to go too far. Then it'll correct a little bit, it'll correct too much, and then over time, it'll just get lower and lower and lower, and then it will stay at this state. And where it starts just kind of staying in a constant state, that's called equilibrium. And it basically means that some of it is existing as HCl, which is this, and then some of it is existing as the H plus ion or the Cl ion as well. And where that, based on the kind of forces that are pulling the H plus away or pushing the H plus back onto the Cl, that's where the equilibrium will happen, and that will be very different for each kind of molecule that we're dealing with. So let's just go through a few of these equilibrium constants is what they're called. So the first one, which we've kind of already been introduced to, is called the acid dissociation constant. Now, I told you that Ka is a measure of acid strength, but really what that means is it's the concentration of all the products divided by the concentration of the reactant. So I've just filled it in for HCl, so this should be H plus and Cl minus. So we've got the acid at the bottom, and then we've got the amount that we've split into at the top. Now, if we just think about HCl, we're probably going to get a lot of these things. We're going to get a lot of products because the HCl wants to split into its ions, and then we're going to have less of this as well because a lot of it splits up. And that's why Ka is a measure of acid strength, because when Ka is high, it means that you're getting a higher concentration of products than the reactants. So if you have a really strong acid, you're going to more likely form those products, which are the two ions, so the H plus ion and the Cl minus ion. So just to recap that, the tendency of something to dissociate, an acid to dissociate into its ions, will mean if it's a strong acid, you'll have more of these products, more of the ions, and less of the acid form. And that relationship drives up the Ka. Just to demonstrate that mathematically, if you had, let's say, 1 over 1, that's going to equal 1, right? Now, if I drive that up, like what we've done here with our products, let's say I drive that up to 5, that's obviously going to increase my Ka. So if I increase my denominator, this is a bit of that proportionality that I talked about in the maths course, but as I drive that numerator up, that's going to increase my value. Now, KEQ is literally the same. It's just saying that you're going to have more products. If you have a high KEQ, it means when you reach equilibrium, you're just going to have more products than reactants. So basically the KEQ is just the acid dissociation constant of things which aren't acids. So if you had something that is more likely to form the products, then that's going to have a higher KEQ. So that's how you can kind of interpret if you need to compare multiple KEQs, you can look at them and then just say the higher one is more likely to have more of the products than the reactants. Okay, so we're going to lump those two together as just products of reactants, either for acids or non-acids. The last one we want to focus on is KSP, and this is called the solubility product. And basically how I think of the solubility product is basically the threshold where things will remain soluble. So remember, solubility is just things being dissolved in the solution. So we just basically multiply together the two concentrations of the products. And remember, all these K values, they're all set. So whatever molecule you're using for KSP, it has its own value. You can't change that. That's just inherent to the molecule. So we're going to have this KSP value, and let's just say that that KSP value is 10, for example. That means that we can multiply together the concentrations of the two products, and if it's under that threshold, we know that they will both be dissolved in the solution. If it's above that threshold, then we're going to have something called a precipitate forming. And what that precipitate is basically, if you imagine you put like a heap of salt or a heap of sugar into water and stir it around, it'll probably all dissolve. But if you put too much sugar in, it won't all be able to dissolve. So that solid that accumulates in a solution, that's called precipitate. And basically, as long as we're under that threshold, we will have none of that forming. So if we had, say, 10 of our first product, that means we would be allowed to have 1 molar of our second product, and that would be equal to the threshold, so it would all be dissolved. We could also have 5 and 2, and that would also be 10. Or we could have 2 and 2. That would be 4. So that's under our threshold. But as soon as we go above that threshold, so if we had 4 by 3 or something like that, we know that there's going to be some precipitate forming.
Okay, I'm going to jump over to some questions now. So the question is to figure out the diameter of the radio bubble, with the context that there have been radio signals sent from Earth over the last 100 years, or starting from 100 years ago, that formed a radio bubble. Given the speed of a light, I'm given the distance of a light year, which is 1 times 10 to the 16 meters, and then I'm given the speed of light, which is 3 times 10 to the 8 meters per second. So what I want to do in my head is just time. So if at 1 light year, I have 1 light year. So my assumption is that, and I did Google this yesterday, so a radio wave travels at the speed of light. I see. Wait, do I see? Wait, so it travels at the speed of light, which is 10 times 10, sorry, 3 times 10 to the 8 meters per second squared. So, but then I have a light year, 1 times 10 to the 16 meters. So kind of just times that by 100. So 100. What's 1 times 10 to the 16? What's that times 100? It's 2 decimals. No, 2 decimals, right? So so it's A. 5A. Pretty confident with that, because 2 decimal places is just adding another another power of 2. So 18 to 18. So A. Let's just check that. I'm pretty sure that's right though. C. C. Hmm. 3 times 10 to the 20. What's 3 times 10 to the 24? Oh wait, the diameter. So, okay. And then I have to know how to get the diameter. the diameter. How do I find the diameter? So, do I have the radius? Is what? The around? I have that. Yeah, I have that. Diameter equals 2. Okay. So it would be B then, but it's not B. So if D equals 2R, then it should be 2 times 10 to the 18. No. I don't know how to get there. Someone drop a comment or help me if they know. let me just explain what I'm doing, and I don't know if it's going to be useful or not, but I'm spending so much time on one question, um, just because I think one of the areas I'm lacking in is the, first of all, the sort of background knowledge to be able to answer the question in the first place. Like, for example, I actually messed up yesterday, like what a diameter was. I actually didn't understand what that was. I thought it was the circumference of a sphere. Whereas when I googled it, I found out that it was just the um, like a crossways measurement of the sphere. So without that knowledge, I wouldn't have been able to answer that question. So that's the first area. And then the second area is the reasoning capabilities. So like how to use that information to then answer the question. And so that takes a lot longer, and I haven't really developed that skill. So I'm kind of just in my mind, I'm just sitting here thinking about how I can answer the question using that reasoning. And I don't know a better way to go around it than just sitting here thinking about, what tools do I have to answer the question, what's in the stem, and it takes a lot of time. Like I've been on this question for like half an hour now, including yesterday. So I don't know a better way to do it, but if anyone has any suggestions, feel free to drop them in. But that's what I'm doing at the moment. And like drawing helps me a little bit as well. So like I'm trying to find the diameter. Um, I know the answer. So the answer is 3 times 10 to the 24 meters. Um, but I don't know how to get there basically. So I'm trying to trace back the steps from the answer. And I also have Google here to help. Like I'm gonna Google stuff if I don't know, but I don't just want to Google how to answer the question because that will basically not. I'm not learning how to reason my way there, but I can use Google to, for example, find out what a diameter is. I guess I just move on to the next question. Either when I get the answer, I've figured out how to reason my way there, or when I just feel like I've exhausted all possibilities of reasoning. Um, and so I feel like that moment's coming soon with this question. So when I run out of new ideas to try, basically. Because I know the answer as well, it makes it a little bit easier. So like when I look at 3 times 10, so to the 24, I can go in my head like, what does timesing 10 to the 24 meters by 3 do? Um, and then what does adding, you know, uh, 8 more powers to 10 of 10 do? That's what I'm doing at the moment. Okay, so I've just picked up on a little thing here. So 3 times 10 comes from the speed of light, and then if I add 8, so 3 times 10 to the 8, so if I add 8 onto that 16, I get 24. But then why am I doing that? I guess my best reasoning is that the wording of the question, so it says, which of the following is the closest to the current diameter of the radio bubble? So the current diameter, um, I understand to be the value of 1 times 10 to the 16 meters over the last 100 years. So that 1 times 10 to the 16 meters is a light year. There's been 100 of them. So whatever that is. And then adding on the speed of light, approximately 3 times 10 to the 8th meters squared. Sorry, meters per second. Yeah, that's tricky. I mean, I'm happy with my reasoning, I guess, because I don't know if I'm going to get better than that. So let's see what thing we can actually use here.
Following is closest to the AW for products with an MFSL of 3 years. Now, this is actually, I didn't actually check this, but I should have. Question 25. So, which of the following is the closest to the diameter of the radio bubble? So, it's saying that we started broadcasting signals into space 100 years ago, and there's now a bubble of television signals. They travel, okay, so in 1 year, they travel 10 to the 16 meters. So now it's saying the diameter of the bubble. So in 1 year, 10 to 16, so 100 years, we'll just be timesing that by 10, by 100, which will.
That's what I originally did. He did the 18 as well. I think that's because there's two zeros.
That'll be like 10 to the 16 times 10 to the 2. And then that's 100 years, but remember that we would be shooting these signals out in one direction. So it means it's gone 10 to the 18 meters this way, but it also means it's gone 10 to the 18 meters that way. So it'd actually be 2 times 10 to the 18 meters
That's what I thought it was.
for that one, which is answer B.
Not B though.
Okay.
B, so I think he's got it wrong. Unless I've got it wrong. 5. Oh my god, it is B. Oh, I've just spent all this time, so dumb, I just spent all this time trying to figure out why it's the wrong answer. That's why we're not getting good marks in the GAMSAT. Well done, well done. 2 times 10 to the 18. It is that. Okay. Well, whoops. I mean, I'm happy that I got it right, but that's very foolish of me. Anyway, I will leave it there. There's just a quick little one today. I'll be probably back. No, I won't be back tonight, but tomorrow we'll be on. We'll be on tomorrow. So I'll wrap it up here and catch you in there.